All right, everyone. Why don't we get underway here today? Welcome back after that 3-day weekend. Good to see you all again. A couple bits of business before I get to talking about biology stuff. First, for those of you who have been coming in a little bit early, the last 2 times we've played some videos for you. I am open to suggestion in terms of what it is that gets played there. So if you have like a favorite YouTube video that's like 5 minutes long, 10 minutes long, how about if you email them to our supplemental instructors? You can find their contact information on the pilot page for the course, and we can crank up some tunes that you guys like better than the things that I think are funny. All right, so that's one thing. And then the other thing is on Tuesday, a week ago, when we first met, I talked with you about the lab manual and the lab for the course. I told you, remember, there were no labs last week. I think everybody has figured that out now, right? But labs do start this week. So come to lab ready to do the first experiment this week. I also told you on Tuesday when we first met that I was going to double check and find out just what it is the people who work in the labs wanted you to have with you. I've gotten that information just like a half an hour ago. Here it is. They want you to bring goggles. All right? Don't worry about gloves. They will provide you gloves. But goggles are the one thing that they really are going to be looking for and expecting you to bring with them. I'll tell you as an aside, they used to have extra goggles that they would rent to students who had forgotten to bring them at some exorbitant, outrageous rental fee. Turns out that that was a health hazard. And the insurance that Wright State has frowned on that, so they don't have goggles to loan you anymore. You must bring your own goggles. I like to think that my glasses protect me from anything like that. If you wear glasses, you could try to make that case. I don't think that you will succeed. I think you'll need to bring goggles even if you're wearing protective eyewear like glasses. So bring goggles to lab starting this week. The other things still apply, the bit about closed-toed shoes and something that protects your legs, so a long dress or pants or whatever you're comfortable with. Bikini bottoms are right out, not accepted in lab this week or any time during this semester. Okay? So those are my 2 little bits of just general information stuff for you. And let's just get right to work then, talking about the topic at hand. Let me remind you, in the last 2 times that we've met, we've talked about 2 fairly different things. I started by talking with you about what it means to be alive, and that's an important topic for a biology class, right? We're talking here about the study of life. And then, in lecture on Thursday, I spent pretty much the whole day the whole lecture talking with you about what it is that you need to take away from the first year, 2 semesters, of a freshman chemistry class to be able to really wrap your head around what's going on in a biology class. I feel pretty good about how that played out. I think I delivered what it is that I wanted to get across to you. Today, we're going to take what I talked with you about on Thursday. There are a couple things that I didn't tell you about at the very end that I'm going to talk with you about as a sort of a ramp up to talking with you about today's topic. But today, it's all about water after that. How it is that water is such an important molecule to living things. The cells in our bodies, yours and mine, range anywhere from 70 to 95% water. Our bodies altogether, the mass of our bodies is 75% water, right? Water is a hugely important molecule, certainly for human biology, but also for all living things that we know on Earth. It is such an important molecule. There's no exaggeration with what I'm about to say. Biologists literally cannot even imagine life developing on a place or in a place where there was not liquid water available. And so when we're looking for life on other planets or moons within our own solar system, NASA's slogan is, and this is straight off of NASA's webpage, follow the water. Because again, we just can't imagine life in the absence of water, and liquid water in particular. And water has some just off-the-charts chemical properties and characteristics compared to every other molecule that we might talk about, and yet one molecule, water molecules, have this amazing range of tendencies. That's what I want to talk with you about today. And what underlies those tendencies is, again, that basic chemistry that I talked with you about on Thursday. So I want to start just by reminding you about some of the things that I talked with you about on Thursday, mention a few other things that I hadn't quite gotten to, and then really get to work talking about what's up with water. So with that said, remember, Thursday, this was the lecture outline that I worked with. At the very end, this chemical bonds business, I didn't quite get to the point where I dropped those three definitions on you. The definition of a covalent bond, I think I mentioned that one. I don't think I talked much about ionic bonds, and I don't remember talking anything at all about hydrogen bonds. Let's do that right now, get it over with, and then talk just about what's up with water. So there's water. I showed you that picture on Thursday. It's a 3-atom molecule, 1 oxygen and 2 hydrogens. And here's the thing. The oxygens and the hydrogens stick to each other. They're linked to each other by what are called covalent bonds. And the formal definition of a covalent bond is this is a sharing of electrons between 2 atoms. Right? So each hydrogen to oxygen bond is a sharing of electrons, a covalent bond that makes up these water molecules. And as I was describing on Thursday, when I'm talking about sharing electrons, I mean what's going on is their electron orbitals are overlapping with each other. So the atomic nuclei get close enough to each other that their electron orbitals overlap with each other, and as a result, the electrons spend some time with both of those 2 atomic nuclei, sometimes with neither, sometimes both on one atomic nucleus, sometimes sort of evenly between the 2. Okay? That's a covalent bond, sharing of electrons. That's the strongest chemical bond that we know of and that we'll talk about in a class like this. This is a very stable relationship. It takes energy to bust those 2 atoms apart. Okay? Stable, strong bond. That's what I mean. It takes a lot of energy to pull those 2 atomic nuclei apart because sharing those electrons makes nature so happy. What's making nature happy is that when a hydrogen shares its electron with an oxygen, is that hydrogen now can start to make a claim in some sense that its outermost shell, the 1s orbital, its outermost shell is completely empty. Because when that electron that's usually associated with that hydrogen nucleus is hanging out by the oxygen, its outermost shell is empty. And on those occasions, when the oxygen's one of its electrons is over more by the hydrogen's outermost shell is completely full. And it's not usually in this state where it's half empty, half full. It's either empty or full. And actually, more often, empty than full. That makes nature happy. That's a big deal. I can see people's eyes are glazing over, right? Let me underscore that. Getting the outermost shell completely empty or completely full is what drives all the rest of this chemistry. That's why Linus Pauling got a Nobel Prize for his book called The Nature of Chemical Bonds. He's the first guy to have written down and really appreciated that that's what's the answer key to all of chemistry and how it is that atoms and molecules and compounds behave. So, check out what's going on in this picture. What's going on in the picture is you see the overlap of the orbitals, right? So that's going on. There's some overlap happening here and some overlap happening here, right? That hydrogen's supposed to be a sphere. Part of the sphere is kind of underneath or part of the oxygen, and the oxygen's supposed to be a sphere, and part of it is overlapping with what's going on with the hydrogen. So there's that sharing, the covalent bonding that's going on. But check out what these arrows are trying to suggest to you. It's something I've been talking about. Maybe the picture helps a little bit more. It's trying to suggest to you that hydrogen's electron is actually spending more time in the direction of the oxygen than it is by the hydrogen. Okay? That's because it's easier for oxygen to completely fill its outermost shell than it is for oxygen to completely empty its outermost shell. Oxygen has 6 electrons in that outermost shell. There's room for 8. So 2 of them, if oxygen atoms can pull in 2 electrons to round out that outermost shell, that's cool. But it would have to shed 6 to empty it out. So it's easier for oxygen to fill its outermost shell than to empty it. That makes oxygen what we call an electronegative atom. Oxygen has a tendency to take electrons up, to pull electrons to itself, as opposed to dishing them out. Hydrogen, again, can go either way. It's not very electronegative. It's just as happy to give up an electron as it is to take up an electron. What was that? I'm talking here about the affinity of these atoms for electrons. In other words, about electronegativity. The more an atom has an affinity for electrons, the more electronegative it is. Okay, so oxygen is very electronegative. Hydrogen, not electronegative. It's just sort of middle of the road. And when you hook up a hydrogen with an oxygen, you not only get these covalent bonds, but this is a special kind of covalent bond. This is a polar covalent bond. And I did mention that right at the end of lecture on Thursday. It's polar because the electrons, while they're being shared, are not being shared equally between the 2 atoms. The electron spends a little more time by the oxygen than it does by the hydrogen. As a result of that, the hydrogens have a little bit of a positive charge associated with them from their nucleus. They're 1 proton. And the oxygen has a little bit of a negative charge associated with it. Delta is the lowercase Greek letter delta. That's what that little squiggle is. That means partial negative charge. Okay? Delta plus is partial positive charge. There's a separation of charge. There's not an equal sharing of the electrons. There is a sharing, but it's not equal. That is a polar covalent bond. And that's in contrast to covalent bonds where there is equal sharing of the electrons. Those are nonpolar covalent bonds. You get a nonpolar covalent bond when you make a bond between 2 atoms that have the same or very similar electronegativities. For instance, one hydrogen relative to another hydrogen. By definition, hydrogen has the same electronegativity as hydrogen. If you make a covalent bond between the 2, you satisfy nature's demand that you have a completely full or completely outermost shell. But because their electronegativities are the same, the electrons spend as much time with both of those hydrogen nuclei. That is a nonpolar covalent bond. Polar covalent bonds end up being what gives water its remarkable characteristics. And I'll show you more and more about that during the course of today's lecture. So there you go. Those are covalent bonds, both polar and nonpolar. I need to talk with you a little bit about another kind of bond called ionic bonds. Okay? Ionic bonds, well, let me take a step back. Remember, I said covalent bonds are the strongest bonds we know. Right? So, by definition, ionic bonds can't be as strong. That would sort of fly in the face of what I just told you about covalent bonds. But they do take some energy to break the association, and there is an interaction. It's just with ionic bonds, we're not talking here about sharing of electrons. We're talking here about simply balancing charges. So check this example out. Sodium chloride, good old-fashioned, simple table salt. The same stuff you use to season your food. Sodium chloride is a pretty simple setup. There's an atom of sodium for every atom of chloride. And here's the deal. Sodium has 1 extra electron in its outermost shell. Its atomic number is 11. right? So there are 2 electrons at the level 1, the lowest energy level around, right? So there's 2 electrons there, and then the next 8 electrons can hang out at the next highest energy level, level 2, but there's 11 protons in that atomic nucleus, and there's 1 extra electron to balance that out. That 1 electron is out there lonely, all by itself, in the level 3 orbital for sodium. Okay? There's room for 7 more, but there's 1 lonely little electron hanging out there all by itself. And talk about a match made in heaven, chloride, or chlorine atoms, have, chlorine's got an atomic number of 17. What's going on there is you'll have 2 of those electrons at the level 1, 8 of them at level 2, and 7 of them at level 3. There's just 1 more that it needs to completely fill out its outermost shell. All right? Can you see what's going to be happening here? Again, it's a match made in heaven. Sodium just has this 1 extra electron. If only it could foist it or pawn it off on something that would take it off its hands. Nature would look so kindly upon the sodium that can pull that off, because its outermost shell would be empty. There'd be a nasty, unpleasant positive charge because the electron's not there to balance out the number of protons, but that outermost shell would be completely empty. Nature likes that. That's a big deal. Chlorine, in contrast, just needs 1 last little electron to completely round out that outermost shell. Talk about electronegative, right? This sets the bar. It pegs the needle for electronegativity. You can't get too much more electronegative an atom than chlorine. It's just dying to pick up 1 more electron. And so you find yourself in the playground with these 2 things hanging out together. One of them's got a ball. The other one really wants a ball. The one with the ball, I don't really care. You like balls? I wish I didn't have to lug this ball around with me. And the other one just, oh, I'm taking your ball, buddy, whether you like it or not. The chlorine sucks up that electron, picks up a negative charge from it, but is happy because its outermost shell is completely full. And the sodium ends up with a completely empty outermost shell and a positive charge. Nature's still not happy about the separation of charge, but if you put that positively charged sodium right next to and rub it up against, perhaps, the negatively charged chlorine, that's not too bad, right? The negative charge from the chlorine and the positive charge from the sodium kind of offset each other. That's not too bad. And you hold those together because of the affinity of those opposite charges, and you make both atoms happy by completely emptying and completely filling that outermost shell. But notice, this is an ionic bond. It's stable. It's held in place because of the interaction of the charges, not because of sharing of electrons. That electron from sodium is gone. It's hanging out all the time with the chlorine. There's no sharing going on that playground, right? So that's an ionic bond, and that can be a pretty stable interaction. It can be busted apart. You can separate the sodium from the chlorine with less energy than it would take to pull apart the hydrogen from an oxygen in a water molecule, but nonetheless, it can persist for quite a long time in nature. So those are ionic bonds. And the last kind of bond that I need to get you guys thinking about a little bit are these things called hydrogen bonds. And they're called hydrogen bonds because hydrogens are usually involved, but interestingly, they don't have to be involved for something to qualify as a hydrogen bond. Let me tell you what it is that I mean. Check out water again. You guys are going to start, I think by the end of this week, having nightmares of that picture of water molecules. It's going to be ingrained in your memory. Your subconscious is going to have a hard time figuring out what to do with that picture because you're going to see it so much today and on Thursday. But there's that old familiar water molecule. Remember, polar covalent bond. The hydrogen has a little bit of a positive charge associated with it. Not a full-blown charge like sodium had, but a little bit of a positive charge. And beneath it here on this picture is ammonia, where nitrogen has pulled some electrons away from 3 hydrogens to round out its outermost shell. And that gives it just a whiff of a negative charge. And this now becomes a happy opportunity for that water molecule, because the water molecule with its little bit of positive charge can rub up against that little bit of negative charge from the ammonia, and both of them can be happy, right? Nature does not like a separation of charges. Now we can scratch that itch by rubbing that little bit of positively charged hydrogen right up against that little bit of negatively charged ammonia. There is certainly no electron sharing going on here. And it's not as strong of an interaction as you would have expected to find between a full-blown positive charge and a full-blown negative charge. For goodness sakes, these are partial charges. Partial charges should interact less strongly, if that's a word, than full-blown charges do, full charges do. But nonetheless, they can interact with each other and they can kind of stick together. There can be an association between that water molecule and that ammonia molecule. All right? That interaction between the partial positive charge of the water and the partial negative charge of the ammonia, that is a hydrogen bond. Now we're talking about interactions, not electron sharing, but interactions between partial positive and partial negative charges between molecules. Okay? So, in the scale of things, nonpolar covalent bonds define the one end of the spectrum in terms of the strength and stability of a bond. And at the other end, we get to these piddly little hydrogen bonds, which are just interactions between partial positive and partial negative charges. Along the way, we've got polar covalent bonds. Then we've got the ionic bonds, and then again we're back to the other end of the spectrum of the hydrogen bonds. Hard to break apart, relatively easy to pull apart, and pretty much everything in between. All of it is governed ultimately by the electronegativity of the atoms in these compounds, and that electronegativity is ruled by this business of how hard is it for you to round out your outermost shell, or to fill up your outermost shell of electrons, or empty out your outermost shell of electrons. That determines everything else. All right, so today let's talk practically about how this stuff plays out. All right, so I hope at this point you have a pretty good sense of what makes water tick, how it is that it has its own special chemical characteristics, okay? And I want to take you by the hand for the rest of today's lecture and tell you about how amazing water is as a result of that fundamental chemistry. What I like to think is that if I did this Socratically, right, if we did this the way that Socrates used to teach, I could just sit down with you and ask you questions. You don't need me to tell you stuff. I think right now, based on what I've told you about bonds and electronegativity and valences, you could figure out everything that I'm going to tell you today just from what you already know. But it's more efficient if you don't figure it out on your own and I just tell you, and then maybe later on you go back and you say, oh yeah, I could have figured that out. Yeah, sure, that all makes sense. It all is consistent. It's all part of what happened in the previous lecture. Right? It just follows naturally from the other things I've talked with you about. That is exactly the kind of mindset I hope you guys have as you're starting to think about the first test for this class. Right? I don't want you to memorize stuff. I want you to be able to say, oh, yeah, well, of course water's going to behave that way because of those polar covalent bonds. That's going to determine that this happens, and in turn that happens. Sure, it all hangs together. Okay, so when I say I want you guys to focus on concepts, I hope I've armed you on Thursday and a little bit this morning with some concepts that you can fight your way through all of this stuff with as I'm talking with you about water. That's what I'm really after. But again, biologists can't even imagine life developing in a place that didn't have liquid water. water does some amazing stuff, right? The outline gives you a list of some of the things. Water's specific heat, you could figure out what's going on with specific heat without me telling you, but when I tell you, I hope there's an audible gasp. It's like, oh, wow, water can do that, right? Again, you can figure that out. If you don't all gasp when I tell you what water's doing, I'm going to assume that you've already figured it out on your own and you've been gasping quietly to yourself, right? But water's specific heat, whoa, no way. How did that happen? That's so cool. Somewhat literally. And then this idea of surface tension and capillary pressure. It's like, no way. The same molecule that does the specific heat stuff is also involved with surface tension and capillary pressure. Wow, that is cool. Now, not literally at all anymore. That was figurative. And then, when we really get to work here, I'm going to tell you about how water does what it is most famous for. It is the single best solvent we know. Multi-purpose, universal solvent. Nothing else does just as well as water does across such a wide spectrum of different things. We'll talk about that by the end of the class today. And again, all of this stuff follows logically, comes naturally from what now I think you understand about how these chemical bonds work. All right, so let's get going at the very top and start by talking about water's cohesiveness. Here's the deal. There's that water molecule again, right? I don't even need to flash the picture. I think I'm going to get you guys conditioned. I'll just say, conjure up a picture of water. When you do that, that's what I'm hoping you'll get, right? So there's water. Got that big oxygen in the middle that's a little bit electronegative, has a little bit of a negative charge, and you got those two hydrogens with their little bit of positive charge. Look what happens. That water molecule by itself is not quite what nature would like. That little bit of negative charge on the oxygen and the little bit of positive charges on the hydrogens, that's a separation of charge. Wouldn't the world be great if you could have that little bit of negative charge rub up against something with a little bit of positive charge just to balance those charges out, right? That would feel so good for nature. Where could we look? Who could we call up to deliver a little bit of positive charge to the little bit of negative charge on a water molecule? What comes of? Oh, wait a minute. How about another water molecule? Wouldn't that be swell? Look at this. Every water molecule, like the one in the center of this picture, has the capacity to make, this is going to blow you away, right? Every water molecule, like the one in the center of the picture, has the capacity to make 4 hydrogen bonds. Like the ones you see happening here with 4 other water molecules. Check it out. That one water molecule has an informal association with 4 other water molecules. I don't see any in here today, but almost always people will have, there's got to be people in the room with bottled water. In those bottles of water, all of the water molecules are hanging out, interacting with other water molecules. There's a water bottle. I knew there'd be some. There's some here too. So those water molecules are all connected together. Now these are hydrogen bonds. They're not strong and they can get separated. You can pull apart the water molecules. You can separate a water bottle into 2 puddles of water if you wanted to. You can break them without too much trouble. But left to their own devices, every water molecule will make 4 hydrogen bonds with something else. And one of the things it's happiest to make the interaction with is another water molecule. How about that? What that translates to in our world, the way we think and what's important to us as biologists, is water molecules stick together. Water molecules don't want to be lonely. They need to have these hydrogen bonds to feel satisfied and fulfill nature's desire for the water molecule. They need to have that little bit of an interaction with other water molecules. If you reached in with super, super tiny tweezers and pulled out one water molecule, you know what would happen? 3 of its friends would try to come along with it. right? There'd be a pull. You'd pull up those water molecules. And you know what else would happen? Those 4 friends that are pulling along with it would also be pulling along 3 more friends with it, with each of them. And you kind of pull the whole bucket out with that one water molecule. They're cohesive. They stick together. That is exactly why paper towels work so well to pick up spills that are water-based. Because what's happening is the cellulose fibers in the towels provide something for a water molecule to hook up with, to make a hydrogen bond with. And that water molecule that makes a hydrogen bond with the paper towel brings 4 of its friends along with it. And those 4 bring 4 more each, and those 4 bring 4 more each, and before you know it, you've got a wet paper towel that sucks up the whole stain. That's also why it is that trees are able to get water from the ground in their roots up to the highest leaves on the tree. It's simply capillary action. One water molecule sticks to the side of a tube, and it brings with it 4 friends, and they keep climbing up because they're bringing on all these friends. You get what are called, it's called capillary pressure. The water actually has a pressure head associated with it as it goes up the trunks of a tree. How about that? So that's because water is sticky and cohesive. And there's other cool stuff that happens because water is sticky and cohesive. There's the tree example for you I was just talking about. How about water striders? They're playing that same game. So water likes to follow its friends, right? But water also doesn't like to have any interlopers breaking apart the associations between one water molecule and another water molecule. And what you can have then is something like an insect, this water strider, that can sit on top of the water, and as long as it's not too heavy, it's not going to be able to separate one water molecule from another, and you can literally walk on water. And it's just because of the surface tension that comes from the affinity of one water molecule for other water molecules. They like to stick together. And you need to invest some energy. You have to exert some force to pull those water molecules apart. That allows stuff like this to happen. At lunch today, think back, a crazy old Dan Crane, and take a little drop of your water bottle or a glass of water that you're drinking. Even a Pepsi will do. We're a Pepsi campus, you know. And put some on the countertop or the table that you're at, or the chair, perhaps, that you're at. Notice how the water will bead up, right? It beads up because that's surface tension. The water molecules are trying to interact with other water molecules, and they pull together to hang out together as opposed to laying flat, like another molecule, like ethanol, for instance, would do under the same circumstances. So surface tension is all due to water's cohesiveness. So is capillary pressure. Pretty swell, neat trick. But let's talk now about some of the energetics associated with water. And I suppose the best place to start is just by introducing you to this concept called specific heat. Here's the thing. When things get hot, what's happening at a molecular level is the molecules move faster. Heat is all about the speed with which atoms and molecules are moving at a molecular level. Something hot has molecules that are moving faster than something that's cold. Plain and simple, that's all there is to it. There's this idea called specific heat. It's a formal thing. It's a measure of how much energy you need to invest in a group of molecules to get them to move faster. And to make it very formal and specific, here it is. It is a specific heat, after all. The specific heat of a molecule or a compound has this definition. It's the amount of energy that you need to invest to cause 1 gram of that substance to increase in temperature by 1 degree centigrade. That's it. Seems to me like the cadence there wasn't right. But the specific heat is the amount of energy you need to invest to raise 1 gram of something 1 degree centigrade. How about that? That's better cadence with that delivery. Water has one of the highest specific heats known to science. There are a couple things with higher specific heats, but forget about them. They're not important biologically. Of the things that pop up in nature and in our lives, and certainly in our bodies, there is nothing that needs to have more energy invested in it to get its temperature to go up, to get the molecules to move faster than water, period. In fact, water defines specific heat. It's the benchmark against which pretty much everything else gets measured. To the point that the definition of a calorie, which is a measure of energy, the definition of a calorie is rooted on the specific heat of water. It's 1 calorie is the amount of energy that it takes to increase 1 gram, or 1 milliliter it happens, of water 1 degree centigrade at room temperature. All right, that's the formal definition of a calorie. If you're worried about how many calories you're eating, you want to lose some weight, nutritionists have a different definition of calorie. A nutritionist's calorie is actually 1,000 calories. Okay? Later on, when I'm talking with you about glucose and the calories and such associated with it, that's going to blow your mind, how much energy is stored in a single glucose molecule. But for now, standard chemical definition of calorie is the amount of energy you need to increase 1 gram of water 1 degree centigrade. Everything else that we worry about tends to have a lower specific heat. For instance, okay, check it out, water's at the bottom there. All the other things on this list of materials have lower specific heats. The reason water has such a high specific heat is because of all of that hydrogen bonding going on between water molecules. There is also some hydrogen bonding that can take place between acetone molecules without even worrying about what that structure looks like, just accept that that's the case. And because there are those hydrogen bonds that can take place between acetone molecules, it has a relatively high specific heat, but nothing like water. Same for ethanol. Do you ever wonder why something metal often feels cold to the touch when you first pick it up and then gets warm, what, a few seconds, maybe a minute at tops? All right, got a metal pen here. It does feel nice and cold. It's refreshing. I'm working up a sweat. You guys are in luxurious comfort. I'm working here, right? The reason that this pen felt cold when I first picked it up and now is kind of feeling gross and warm, I don't want to touch it anymore, is because metal has such a low specific heat. There's relatively little interaction between one metal atom and the next metal atom, and as a result, they get rid of heat real fast, they lose the heat real fast, and they suck up heat really fast. You wonder why, if you do like an isopropanol rub or put ethanol on your skin as a disinfectant, you know why it feels so cold? It feels so cold because those ethanol molecules or the isopropanol molecules take the heat from your body. They suck it up well because they've got a low specific heat. And then they evaporate and they take those high energy molecules, the fast moving molecules, away from you. And that's why I'm sweating. I'm trying to get rid of some water molecules here, right? That's why evaporative cooling works the way it does. So there's this buffering of temperature. You have to put more energy to change the temperature of water. You need to invest more energy to change the temperature of water than just about any other material that you encounter. Off the charts, it defines one end of the chart, essentially, of specific heat. And one of the consequences of that is temperature buffering from bodies of water. All right? This is a weather chart or a weather map off of Southern California. The Pacific Ocean tends to be cooler than the surrounding land, right? And what happens then is that the heat that would have otherwise been associated with the land gets pulled into the ocean, and vice versa, the slower moving molecules from the ocean cool down the land, and you get these more comfortable temperatures right by the coast as opposed to what you would find further inland. It's another large-scale example of temperature buffering. But the coolest by far, and the one that's going to make you gasp, if you haven't stopped to think about this already, is what happens with frozen bodies of water. This is mind-boggling to me. How this could have come to be, wow, what a neat trick is going on here. Can you guys think of any other substance that is denser in its liquid form than its solid form? That's just not the way the world seems to work. But that's how water works. Liquid water is those little V-shaped molecules bopping around. Get that mental picture of water again. There are a few smaller versions of it here for you to, jog your memory with. Liquid water, these V-shaped molecules, sometimes they can bump up against each other so that the crotch of one is bumped up against the crotch of another, right? That gets two water molecules in pretty close proximity to each other. That's pretty high density. It's the number of atoms per unit space, right? Because they can interact with each other that way sometimes, that's a fairly dense opportunity. But solid water doesn't have any of that crotch bumping going on, right? That could be the quote of the day for the class, right? You want to make sure that's only used in context, right? Solid water doesn't have any of that stuff going on. Instead, with solid water, the molecules are moving now so slowly that they lock into place with their hydrogen bonds. You don't break those hydrogen bonds anymore. Every water molecule hangs out with 4 other water molecules, and there's no wiggling and no crotch bumping going on. It is those rigid hydrogen bond 1 to 4 kind of network thing, and that's it. And because of that, you don't have that high density situation, and solid water then has a lower density than liquid water. Pretty cool. Solid water, ice. Now we're talking about water molecules with the lowest energy you can get, right? They're not moving at all relative to each other. That's pretty low energy. That's a low temperature. Liquid water, the molecules are moving at least a little bit, sometimes a lot, and that means they've got more energy and a higher temperature. So the bottom line, let me make sure everybody's with me on this, right? The bottom line is because ice is less dense than liquid water, ice floats. Ta-da, right? You could have predicted that just based not on your past experience, but based on what we've been talking about the interactions between water molecules and temperature and hydrogen bonding, right? It just seems to follow naturally. You didn't need me to tell you that ice floats. You knew already. I know that. But if you set that aside, now at a molecular level, you can play it all out and say, yeah, of course, ice has to float. It's less dense than liquid water. And now, get ready. This is it. This is going to just change your life forever. Because ice floats, water is an even better temperature buffer than it would have been if ice didn't float. It sounds anticlimactic, but that's it. That's the big payoff here. That's a big deal. What other liquid forms a solid that is less dense than the liquid? I can't think of any. Water's the only thing I can think of that fits that bill. And check out what that translates to from the perspective of a biologist. The molecules of water that have the least energy associated with them go to the top of the freezing container or the lake of water. That's a big deal. The least energy molecules are the ones that are at the top, and the higher energy molecules are underneath them. That puts the kibosh on the potential for evaporative cooling. Because the way that evaporation cools you and cools a body of water is the higher energy molecules of water get to move. They bump into each other and transfer energy from one to another. Some of those high energy water molecules get to move so fast that they don't just break one or two of their 4 hydrogen bonds with other water molecules. Get this, they break all 4. And when a water molecule breaks all of its hydrogen bonds with all of its nearby friend water molecules, we got a word for that. We call that steam, right? This is gaseous water. If a water molecule breaks all of its hydrogen bonds with all the rest, it's out of here. And it takes with it all of its extra energy. That's how evaporation ends up cooling you off. It's because the highest energy water molecules, the ones that are moving the fastest, leave. And by definition, everything that gets left behind has less energy, and it has less energy because some of its energy was imparted to the molecule that left the party. But that can't happen with a body of water that's getting a layer of ice on the top of it. The least energy-rich molecules form a barrier. They can't evaporate. They're locked into 4 hydrogen bonds with other water molecules. There's nothing to break free there. They can't break free. They don't have a lot of energy, and they've got 4 hydrogen bonds. The guys with energy underneath them can zip around all they like, but even if they break the hydrogen bonds with all of their friends, they've got nowhere to go except bump into another water molecule and transfer some of that energy to the other water molecule and heat up the rest of the water molecules. Temperature buffering because of ice is amazing. If lakes in this part of the world froze, Ohio, if lakes and rivers froze from the bottom up, there wouldn't be a fish alive in Lake Erie or anywhere else that you care to go fishing. Because if ice was denser than water, the whole lake, the whole river would completely freeze. There'd be nothing, no liquid water for the fish to hang out in and metabolize with and hang out with, right? It just isn't a workable system. But because by happenstance, water has this quirky hydrogen bonding capacity that it does, cute little shrimp can live even in frozen bodies of water because the highest energy guys, the highest energy water molecules get trapped beneath that buffering layer of ice. I just, I want to take my microphone and, that's it. I got nothing better for you for that than what I just said today. That's the high point of the lecture. So thanks all for, here, I got more I can tell you, but boy, to me, whoa, that is huge. And that is not something that I think I would have taken the time to figure out, but again, it's the sort of thing that with the knowledge that you guys now have, these concepts we've been talking about, I think you could have predicted exactly that, and that's something that if you had predicted it that way, you'd say, yeah, but that just can't be right. I must be missing something. You're not. You know everything you need to know to figure that out. Okay, so water, it's sticky, it's got this cohesiveness to it, capillary pressure, surface tension. Water's got these very unusual heat capacities. It's got this, off the charts almost specific heat. But what water is really famous for is it is a solvent that's better than any other. Medieval alchemists were all about 2 things. It's actually the foundations of chemistry. One of them is they wanted to find the philosopher's stone, some compound that would let them change base metals into gold, right? That'd be cool, right? But the other thing, and it doesn't get nearly as much attention, is they were also looking for something called aqua regia. So there was the Philosopher's Stone and aqua regia. Aqua regia was this mythical, aspirational kind of solvent that could be used to dissolve the regia, the noble metals. Something like gold and silver and platinum. Alchemists couldn't find anything that could dissolve those noble metals. And at the same time they were trying to convert base metals into gold, they also wanted to find something that could dissolve those noble metals, particularly gold, but they'd be happy for silver and platinum as well. All right? The single best solvent that they could find is aqua regia, was aqua, water, right? Water was the best solvent that thousands of alchemists working thousands of hours could come up with to dissolve stuff. Water is an amazing solvent. Now, let's see if I got a picture for you here that shows you exactly why that's the case. I happen to have such a picture. Remember sodium and chloride, or chlorine, sodium chloride, the two together. Check out what's happening with sodium and chlorine. You don't need me to tell you it's pretty easy to dissolve salt in water, right? You can get a lot of salt dissolved into a little tiny bit of water. The mechanics at a molecular level for why that's happening, again, I don't think you need me. You can figure this all out on your own, but let me help you here if you're wanting to be lazy, all right? The chlorine has a negative charge associated with it. It's got this sort of stable relationship with the positively charged sodium, but nonetheless, nature doesn't like it because that, you can hide it by putting it near a positively charged sodium, but the reality is that chlorine's got a pretty flaming negative charge associated with it. But look what could happen if you let that chlorine interact with water molecules. Those water molecules can rub their positively charged, partially positively charged hydrogens up against that negative charge, and they can swarm it, right? They can wrap themselves around it and say, oh, look at this. You'll be loved and happy with us, Mr. Chlorine. Come away with us. And the water molecules don't think this is too bad a deal, right? They're used to hanging out with other water molecules and the slightly negatively charged oxygens, but man, what they really want is to be with the star, the biggest, the strongest negative charge they can find, and chlorine just puts to shame any other partial negative charged oxygen that it might encounter. This is looking pretty fun, pretty cool. This is a party the water molecules would love to be invited to. The chlorine is getting swarmed by adoring water molecules. The water molecules are in the presence of greatness with the negative charge, and off goes the chlorine atom, and all that's left behind is that poor positive lonely sodium, but it's happy too because there are a whole bunch of partial negative charged oxygens that would just love to be with the star of positivity like sodium. That sodium gets wrapped up, the oxygens rub up against its positive charge. Everybody is happy. Water is a super awesome solvent. It's one of the best things at dissolving things that we know of. Technical jargon for you. A solvent dissolves stuff. A solute is the stuff that gets dissolved. Okay? So here, the sodium and chlorine, the sodium chloride, the salt, that's the solute. The solvent here is water. In biology, when we're talking about a solvent, unless somebody goes way out of their way to tell you it's not water, the solvent is water. Okay? Just as a formal declaration, unless I tell you otherwise, and I'm talking about some solvent, that solvent's water. Now, chemists over the years have appreciated that you need to do some bookkeeping with solutes and solvents, and so they get pretty particular about measuring concentrations of things, how much solute got dissolved by a solvent into a solution. And that nomenclature hangs on, it revolves around this idea of molarity. This is one of the more boring bits of trivia that comes from chemistry, but let me throw this out at you. A mole is 1 Avogadro's number of molecules. Okay, so for any given molecule, let's talk here about sodium chloride, for instance, like the one on the screen right now. Each sodium chloride molecule has a molecular weight of 58. That means that between the sodium and the chlorine, there are, if you count them up, a total of 58 protons and 58 neutrons. That's the molecular weight of sodium chloride. If you give me an Avogadro's number of sodium chloride molecules, you will give me 58 grams of sodium chloride. How about that? 1 mole of a compound is equal to that number, is equal to the molecular weight of that compound in grams. The molecular weight of sodium chloride is 58. 58 grams of sodium chloride is 1 mole. That's 1 Avogadro's number. If you're really a glutton for punishment, an Avogadro's number is 6.023 times 10 to the 23rd, something like that. It's an insanely large number of molecules. But here's something kind of cool. 1 mole of sodium chloride is 58 grams. 1 mole of sodium hydroxide is 40 grams. The total number of protons and neutrons that come together to make sodium hydroxide, a different compound than sodium chloride, is only 40. And so 40 grams of sodium hydroxide is 1 mole of sodium hydroxide. 58 grams of sodium chloride is 1 mole of sodium chloride. Okay? So I'm just throwing out some examples for you there. Where I want to go is this. If I took 58 grams of sodium chloride, 1 mole of sodium chloride, and I dissolved it in 1 liter of our favorite solvent, water, I would have what we call a 1 molar solution. Okay? 1 mole of the solute is dissolved in 1 liter of the solvent. That's a 1 molar solution. I'm going to take a chance and do some math on the fly here. 58 divided by 2 today to me feels like 29. Okay? If I took a half a mole of sodium chloride, let's say 29 grams, and dissolved it in a liter of water, I would have a half molar solution. I'm going to take another chance and say 2 times 58 is like 116. If I took 116 grams of sodium chloride and dissolved it in a liter of water, that is a 2 molar solution. All right? So molarity is something we can use to keep track of just how much solute is dissolved in water as a solvent. Okay? So there's some concentration. Here's the mechanics of it for you. And there's that water molecule that we keep talking about. All right? I told you emphatically just half an hour ago that water molecules have this really happy situation going on where the hydrogens are satisfying of need of the oxygens and vice versa. They make these covalent bonds. I qualified it a little bit, and I said, they're covalent bonds, but they're actually polar covalent bonds. Okay? Unequal sharing. Sharing, but unequal sharing. Well, I need to qualify it just a little bit more right now. Okay? Because even in the most stable sharing relationships, sometimes one of those bonds might get broken. What happens with water is once in a very rare occasion, the electrons that are being shared between a hydrogen and an oxygen stop being shared. The electron just ends up spending all its time with the oxygen. When that happens, if there's not sharing going on anymore, it's not a bond, and the hydrogen goes off on its own, separate from the oxygen and the other hydrogen that it had been bonded to before. those bonds can break. Sometimes the sharing just doesn't work out quite that right, and you separate, and the bond is broken. Again, that happens extremely unusually. It's not a common occurrence. Only 1 in 554 water molecules at any given point in time have had this nasty breakup take place. Okay? When it does happen, though, you end up with a lonely, naked, cold proton, positive charge, all by itself, and a hydroxide ion, an oxygen with a hydrogen, with that extra electron giving it a negative charge. Two of them have gone off in their separate directions. Both of them are pretty chemically reactive because they both aren't quite whole. They need to interact with something else. You could think of them as sort of a loose cannon on the deck of the solution that you're talking about. That hydrogen really wants to do something to balance out its positive charge. It's itching to find something negative that it can latch onto. And vice versa, that hydroxide ion has that negative charge, and it just doesn't like that, and it's got to find something positive it can latch onto. They're motivated, very chemically reactive molecules at this point. But again, where I want to go with all this is that it doesn't happen that often. Only one molecule out of about 554 million does it happen to. And yet they're very reactive, and so they get the attention of chemists and, by extension, biologists. Because they are so reactive, we often find it's important to keep track of just what concentration of hydrogen and hydroxide ions is present within any given solution. Okay? Because they're so reactive, we fixate on their concentration. We give a lot of attention to their concentration. One molecule out of 554 million translates to 10 to the -7th molar. Okay? I've talked with you about molarity. 10 to the -7th. 10 to the -6th is 1/1,000,000th of a mole. 10 to the -7th is 1/10,000,000th of a mole of hydrogen ions is dissolved in any liter of water, pure water, that you might happen to have. Teeny tiny concentration, 1 × 10 to the -7th mole. And yet, because that hydrogen ion and the hydroxide ion that are associated with it, that must come, whenever you've made that hydrogen ion, you must also have made a hydroxide ion. Because those two things are so reactive, we pay a lot of attention to them, to the point that there's this whole nomenclature that's built up around hydrogen ion concentrations in a solution. And it gets cumbersome to talk about 1 × 10 to the -7th molar hydrogen ion. Right? So the chemists have delivered to us a shorthand, and instead of saying 1 × 10 to the -7th molar hydrogen ion, they would have us say a pH of 7. Lowercase italics p in upper level math classes is shorthand for the negative logarithm of something. Okay? 10 to the -7th, the negative log of 10 to the -7th is 7. So you put that lowercase italics p in front of a capital H, and you strip away the plus sign from the upper right, just because we want to do this quickly and easily. And what we're talking about, something that's a pH of 7, what that means, in other words, is this is a solution that has 1 × 10 to the -7th moles per liter of hydrogen ions in that solution. So that's what pH 7 means. pH 7 is what happens, that's neutral. That's just what happens with water. And if you're worried that the OH isn't getting enough press here, right, that's equally as important. If the pH is 7, the POH, right, same jargon, the POH is also 7. How about that? So if I tell you pH of something is 7, you could fill in the gaps and jump ahead of me and say, oh, the POH must also be 7. In fact, it happens so fluidly that most people don't ever even bother talking about the POH. They just say, here's the pH, and then you figure out for yourself what the POH is, because if it's pH of 7, the POH is 7. And here's the rule that'll let you figure out all the rest. pH plus POH must always equal 14. So if I tell you something's got a pH of 5, the POH must be 9. In fact, I hope it's so obvious, or becomes so obvious, that you won't be surprised that I don't even bother telling you the POH, because I told you the pH. Do I need to tell you the pH 2 times? It's the same thing as telling you pH. pH of 5 means the pH is 5. It makes just as much sense to say that as saying the pH is 5 and the POH is 9. Right? They're synonymous. It couldn't be anything else. Really? Why did you bother telling me the POH is 9? You just told me the pH is 5. This becomes redundant. pH plus POH must always equal 14. And the reason for that is pretty straightforward. Again, another thing you probably don't need me to tell you, but think about it this way. If a solution has more hydrogen ions in it than hydroxide ions, well, let's just focus on the hydrogen ions for a second. So if I change the hydrogen ion concentration from 1 times 10 to the negative 7th moles per liter to something like 1 times 10 to the negative 5th moles per liter, what that means is the pH goes from 7 to 5, but it also means that the concentration of hydrogen ions has gone up, right? 1/100,000th of a mole is more than 100 millionth of a mole, right? We're talking about fractions here, so that's still tiny, but it's more. It's actually 100 times more. It's like the Richter scale for earthquakes, right? A magnitude 6 earthquake is 10 times stronger than a magnitude 5 earthquake. A pH of 7 has 1/10 the hydrogen ion concentration of something with a pH of 6, and 1/100th the hydrogen ion concentration of something with a pH of 5. These are logarithmic scales. So if I've done something to a solution to increase its hydrogen ion concentration, what that also translates to is that since there's more hydrogen ions floating around, they gobble up, they interact with, they hook up with, if you like, the hydroxide ions more readily, and they reduce their concentration from the solution. So at the same time you're jacking up the hydrogen ion concentration, those hydrogen ions are seeking out and interacting with hydroxide ions with a vengeance, and they bring their concentration down. If the pH goes to 5, the POH gets less still, lower concentration still than it was before. It goes to 9. If you make it something pH 1, the POH becomes 13. pH plus POH always equals 14. Okay? So how am I going to jack up a hydrogen ion concentration? Well, easy. I'm going to put some acid in there. All right? That's the definition of an acid. An acid is something that increases the hydrogen ion concentration. Here's a nice, clean, simple example of an acid for you. We've talked a fair bit now about sodium chloride. Well, that's a salt. It is salt, but it is also an example of a salt. Here's another salt for you. All right? Salt is just one positively charged thing hanging out with a negatively charged thing. That's what the definition of a salt is. Sodium and chlorine fit the bill pretty well. But here's another salt for you. How about hydrogen chloride? A hydrogen hanging out with a chloride. The hydrogen loses its electron, gets a positive charge, hangs out with the chlorine, which has a negative charge. That's a salt. If I take hydrogen chloride, also known in the trade as hydrochloric acid, if I take hydrogen chloride and I put it into water, I'm just giving a shot in the arm to the hydrogen ion concentration. There's no hydroxide coming along with it, right? It's just hydrogen and chlorine. I can increase hydrogen ion concentration easy by putting in something like hydrochloric acid. And if I do that, again, those extra hydrogen ions are going to be seeking out hydroxide ions, and they're going to hook up and get back to being water again. And at the same time I'm increasing the hydrogen ion concentration, I will be decreasing the hydroxide concentration. And so here's what's the star of this week's lab. All right, so in lab this week, it's all about playing with pH. Pure water by itself has a pH of 7, but you put other stuff in it, like hydrochloric acid, which isn't on that list, but things like ammonia are on that list. All right, that's a common household thing. Ammonia, we say, is a base because it reduces the hydrogen ion concentration. Lemon juice and battery acid, there's a good one, those are acids because when you put them into a watery environment, they increase the hydrogen ion concentration. A solution that has a pH of 7 and also a pOH of 7 is what we say is neutral. That's neutral pH. If the pH is less than 7, we say it's acidic. And it's probably because you put some acid in there. And if the pH is greater than 7, we say that it's basic. And it's probably because you put a base in there. Okay? And so in lab this week, the lab is all about playing with pH. Figuring out what different things do to pHs. You're going to get to play with compounds called buffers that cause it to be harder for the pH to change, right? Some of that gets explained in the lab manual, but you're also going to get a choice of, I think it's 10 different things, common household items, that you'll be able to see what effect they have on the pH of stuff. And as an aside, I give so much of myself to this class, right? You know, you guys should be feeling sorry for me. I tell you so many personal details. To my knowledge, I am the only faculty member in the entire university who gives their entire class beer. All right? If you don't find beer waiting for you in lab this week, I want to hear about it, and I'll talk to the people in the prep lab, and we'll get you some extra beer for subsequent labs, because that's one of the things that you get to check the pH of. Every year it's a fight between me and the people working in the prep lab. Oh, we can't give students beer. It's like, by golly, you're going to give them beer, right? I don't care what their age is. I don't even care what kind of beer it is. My personal preference for this experiment is Old English 800, right? Kind of a lowbrow kind of beer, but works great. You can buy a 40 for, what, $1.99, right? 8-ball for everyone in lab this week, right? But anyway, you'll get to check the pH of a bunch of different household things that you'll be encountering. You'll get to see how those concentrations of hydrogen ions differ from one cell to another. So these are all things that I've just been talking with you about, and I think we've come pretty close to the end of what I wanted to talk with you about today. So, at the end of the semester, when you guys are whining to me about keeping you here right to the edge of class and maybe a minute or two late once in a while, I'm going to look back and say, well, they forgot the third lecture, didn't they? Because I think we're about 5 minutes early. But why don't we call it a day? Go out, have fun in lab this week. I'll see you on Thursday, and we'll talk more now about what's going on with carbon in the context of water. See you guys later.